All right, so energy generation. Last time we talked, we kind of wrapped up talking about thermal resistances. Now we're going to get into this idea of energy generation. If you've taken thermo, right, that should be a problematic statement for you. What is energy generation? Well, you should know from thermal, there is no such thing as energy generation. Energy is a conserved quantity. So it's neither created nor destroyed. It has to be conserved. But here, the important operative word is thermal. Or you can have different forms of energy. What we're talking about here is thermal energy generation. So within some volume of material, you have energy that's converted from one form to another form, or to thermal energy. So just examples of that, things you might be most familiar with. So electrical. So you have like a wire, right? Or some conductor, and you force an electric current through that. The conductor has a resistance associated with that, so that resistor dissipates thermal energy in the volume of the material. So you have electrical energy that's being converted in the volume of the material to thermal energy, and then that thermal energy has to go somewhere. We have to do something with that thermal energy. So it looks to us, when we're doing this as a heat transfer problem, as if you're just magically generating thermal energy out of nowhere, right? So we have electrical energy. Other examples, you might have chemical energy. You might have a reaction occurring within the volume. You might have a nuclear reaction. So a nuclear fissile material will be radiating heat to its surroundings in a volumetric sense. Right? This is occurring within the volume of the material. You can certainly have that. You might also have absorbed radiation. So you have let's say you have a lens, right? Some kind of a semi-transparent or mostly transparent thing. You hit that lens with a really high flux from, say, the sun or concentrated light or something. There's going to be some degree of absorption within that volume. Again, that looks like you're within the volume converting energy to thermal energy. So those are all possible examples of thermal energy generation. All right. Normally, when we're given thermal energy generation, we're given this coefficient G dot triple prime. Right, the watts, or the units on this are watts per cubic meter. Right, watts per cubic meter. So this could be a constant. It could be something where we're saying, if you give me a cubic meter of material, the entire uniform, it's a uniform energy generation within that cubic meter of material, and it's equal to this many watts, right? So G dot would be 2 or 4 or something, whatever the number is, and that's uniform throughout the entire volume. If you have an example like nuclear radiation or absorbed radiation, that's typically not uniform. It's happening more at the surface, and as you absorb radiation, the amount that's available further into the body is reduced, and so you get kind of an exponential decrease. So G dot could be a function of X, Y, Z, or whatever coordinate system you have as well. But this is something that we use in order to describe our thermal energy generation. Okay, so what we're going to do to talk through this process, it follows the same process, really. The analytical process is very similar to what we did for just 1D steady state conduction. Right, we're going to solve the same type of analytical problem today, but we'll just do it through using an example. Okay, so here's an example. So we're in Wisconsin. We're in the Midwest. There's lots of farming going on. If you drive out in the country, you might see these long, cylindrical, white, plastic-wrapped hay bales. Right? It turns out that when you bale hay, if you don't get enough of the moisture out, the hay is actually still sort of semi-alive. And it generates heat as it slowly dies and starts to decompose. So there's within the hay bale, it's generating energy, and it would be at a pretty low rate. Like you look down here, we have our G dot at the bottom is G dot 2 watts per meter cubed. Right, 2 watts per meter cubed is not a lot of energy, but it's significant. And in fact, if you get a bale that's big enough, the internal temperature, because hay is such a bad conductor of heat, the internal temperature can get hot enough where this thing will start on fire. Right? If you got these things in your barn, that's not a good deal, right? Or you just don't want things spontaneously combusting in your cornfield either. So So people, you need to think about how you design or how you actually limit the construction of these hay bales. Construction, a generous word, but what's the maximum size that you can have on a hay bale? What if you have a certain generation, in order to keep it from starting a fire, basically. Okay, so here's some information we're given. We're saying, let's see. So out here we have convection. Right, so we have a convection to the surroundings. The surroundings, let's say it's a relatively warm day, 20 degrees Celsius. The bale's radius is 5 feet, so it's a pretty big bale. And then it's wrapped in this plastic, right? The thickness of the plastic is it's a very thin layer. It's kind of like heavy duty saran wrap type deal, but it has really low conductivity. So we need to maybe consider that as well. Okay, the conductivity of the bale itself is very, very low, 0.04. And again, there's thermal energy generation occurring. We decide that in the past, we've observed that bales above 170 degrees Fahrenheit start on fire. So that's our limit. We can't have at any point within the bale that temperature. Okay, so let's solve this problem using the analytical approach that we started with in a couple lectures ago. Okay, so let's draw out. Let's see if I can draw here. So here's a portion of the hay bale, right? And I'm gonna, let's say, this over here is the center point. So I'm gonna draw a differential control volume. So what does a differential control volume look like in a cylindrical coordinates? Well, it's a thin shell, right? So sorry, it's not very good, but this is my differential control volume, and this differential control volume spans the entire distance all the way around. But there is no temperature gradient in the circumferential direction, right? As a function of theta, there's only a temperature gradient as a function of r, the radius. So the differential element I'm drawing has differential width, dr, and it spans the entire length around. Okay, so what's happening here? Well, we have heat flow going in to that control volume. We'll call that Q dot at R. By the way, sometimes I'll write it, shorthand this as I just wrote it, but really what I'm saying is Q dot in the R direction, right, at position R. Right? That's really what I'm saying. Q dot R at R, or coming out here we have Q dot at R plus dr. Right? That's just another way of saying Q dot in the R direction at R plus dr. Just so you're not confused about that. Okay, so we have heat flowing in, heat flowing out, but now we have generation to worry about. Okay, so I'm going to put here G dot. We have G dot in this control volume. Note that I did not put G dot triple prime. Right? The units on G dot are watts. So we need to somehow convert G dot triple prime, which is given to us as a constant, into G dot. Okay, we'll get to that in a second. So let's do our energy balance. So we're going to say Q dot at R. So things coming in plus things generated, G dot, are equal to things going out plus things stored. So Q dot R plus dr, and nothing is stored. So that's our first law energy balance, our control volume energy balance. And then we're going to use our expansion of Q dot R plus dr. And this is the same thing we did before. And we'll say that we have Q dot R plus G dot is equal to Q dot R plus dq dot R dr times dr. Right? That's the right hand side is our expansion of Q dot R plus dr. Using the limit as, or the derivative using the limit as dr goes to 0. Okay. Now we need rate equations. Well, first of all, okay, this goes away, right? And we're left with the expression that G dot is equal to d Q dot R dr times dr. No, we can't cancel out dr because there's G dot on the other side. Right? Before we could cancel it out and we were just left with dq dot dr equals 0, we still have to keep dr because we have G dot. Okay, so let's come up with some expressions here. What is G dot for this problem? So G dot for this problem is going to be our volumetric generation rate, G dot triple prime times the volume. So what's the volume of my little differential control volume here? right? It's going to be, well, what's the shell's length, let's say? That's 2 pi times r, times what's the shell's thickness, dr, right? Times how long is this thing? Well, I guess, are we given it? It's like L, right? We'll call it L. So if you kind of look at that and make sure you understand it. So we have the shell's circumference times the differential width. And like, so why do we not say, well, it's, pi r, pi r plus dr squared minus, when you have a differentially small width, you can make this approximation very accurately, that it's just 2 pi r times the width. That's a very accurate approximation. Okay, so that's g dot. So now we can plug that in here. That's equal to q dot r dr. And now look what happens. So now we have dr on both sides. You should almost always get to this situation where you can then cancel out that dr. So here we are. We've canceled out our drs. And we're left with the expression. So let's also, let's see, what else are we going to do here? Yeah, so here we are. We have our kind of expression. We'll just write it out. It's dq dot r dr is equal to 2 pi r L g dot triple prime. Okay, so there's our ODE in terms of heat transfer. Okay, remember there's kind of two categories of ODEs that we're dealing with here. One is our ODE in terms of heat transfer. This is usually a really intuitively easier one to understand than the ODE in temperature. So here what we're saying is dqdr, right? That's the change of heat transfer across this control volume. That is, before when we did this, we went through the same process. We said this is equal to 0. Okay, but now and what that is saying is dqdr, so that's not changing, right? Over the control volume, it's not changing. Here now we have this situation where it's equal to something. So that's just telling us intuitively that heat transfer is changing as it goes over this control volume. So every time I have a control volume, I have a term in that I have to deal with. It's actually adding heat to it, to that control volume, right? Which makes sense because we're talking about generation.